Hi, can you hear me? Oh, invalid again. Can you guys hear me? Not actually verified. Where am I going? Here. Boleh dengar ke? Boleh dengar ke? Hello. Right, thank you. Alright, Nyam Yi Mei. So please scan your attendance first. Teo Jia En, Kang Yong Jun, Tian Hian Yong, Chan Lu Tung. Okay, lagi. Nur Amira, Si Shuyan, Shu Kai Bing. Hmm, Baik. Tadi dah ada kan? Hanya B. Macam lutung ni. Yang syutung, Cinagian, Bejialiang. Okay. Okay, can we start our class? Is it okay? Right, boleh ke kita start kelas ni? Boleh dengar ke? Hello, hello, testing.
Boleh, doktor, boleh.
Boleh, right. Okay. Nanti in the middle of the lecture, I will confirm your attendance lagi sekali, eh. Right, I will call your name kalau just to have some discussion lah. Right, chapter 2, hydrostatic force, just to review, right? Subject fluid mechanics, hydrostatics, meaning we want to understand the force because of um, not moving fluid on a structure. And the application is, where is the application? We can't see the application. We've gone through all of this before. Oh, the application is when we want to design dams, for example, dam or empangan. Empangan, we want to retain water. So the height of the water will give significant force to the wall of the dam. So we have to calculate the force. So we have gone through this. In the end, this is the important bit. Oh, sorry. Here, the change of pressure. The change of pressure as you go deeper is equals to rho g times by the change of elevation. Right? As you go deeper, the pressure will increase. And this one, if you remember, we derived it together. We have a prism there, and then we have pressure in the S direction, pressure in the X direction, and pressure in the Y direction. And then you can see the summation of force in the X must be equal to 0. The summation of force in the Y direction must be equal to 0. This is equilibrium of force. Why is it equal to 0? Because the fluid is not moving. Right? This is the starting point is F equals to ma. If you remember Newton's second law, the summation of forces must be equals to mass times acceleration, ma. But if the fluid is not moving, though, so you don't have any acceleration, so you don't have the ma, then it's going to be 0. So then for example, summation of force in the x direction, what do you have in the x direction? You have the pressure in the x direction, and also you have the pressure on the surface of S, but you have to find the x component. So those are the two forces in the x direction. On the y direction, you have Py, pressure due to y, and then Ps, but the y component, and then you have the volume, the weight of the volume of the water itself, rho GV. So we have derived this and we have found out that in the end, pressure in the x direction, pressure in the y direction, and pressure in the s direction, meaning all direction, is the same, assuming the element, this prism, is very small. Right? If it's very small, only 1 point, the pressure is the same. So this is called Pascal's law. And this one, we also derive together. This is to find the equation that we learned before. Change in pressure equals to rho g, Z. So we just skip this part. In the end, we get P equals to rho g, Z. So pressure, we have three terms, atmosphere, absolute, and gauge pressure. Atmospheric pressure is the real pressure at datum. Absolute pressure is actual pressure at a given point, and gauge pressure is the difference between absolute pressure and local atmospheric pressure. Right? I've told this last week. Now we are experiencing atmospheric pressure of 101 kilopascal. We are here. Most of us are here. We are experiencing pressure of 101.3 kilopascal. So this is atmospheric pressure, and it's the reading of absolute pressure, 101.3. If I mention what is the gauge pressure, so the gauge pressure is basically the difference of the pressure minus by the atmospheric pressure. So the atmosphere and the gauge pressure here will be 0. If you go higher, the gauge pressure will be negative. If you go deeper, the gauge pressure will be positive. So because we are already accustomed, kita dah biasa dengan pressure around us, we don't feel there's any pressure, air pressure. So we just use gauge pressure of 0. This one is to show that pressure only depends on Z. Pressure only depends on the height of the fluid above you. It doesn't depend on the height of water below you. It doesn't depend on the shape of container, right? And then we did some simple calculation. Right. This is work example that you guys did last time. So I did mention to you, if anybody can try to figure out why the air pressure here, the pressure here, the pressure here, doesn't matter which Z, doesn't matter which elevation, and the pressure at F is the same, right? Because you calculated the pressure at F, you get negative 13.2. So the pressure here is negative 13.2. So it's suction here because it's negative, you have suction pressure. B, air pressure in the right side of the tank. So when you look at the answer for the air pressure inside of the tank is the same as the pressure at F. So has anybody figured out why this happens? Kenapa pressure dekat F tu sama dengan pressure air above it, even though the Z is different? Right. Anybody who thinks they got the answer, they can just WhatsApp me, right? For some bonus mark, For some bonus mark. It's very simple actually, It's very simple. Okay, now for today's class, we are going to learn about pressure measurement equipments. The equipment that we use to measure pressure, we have barometers, we have piezometers, we have manometers. For manometers, we have three: simple manometer, differential right U-tube, differential inverted U-tube. But for all these pressure measurements, the concept is the same and it's very simple. Just apply the concept, you can use these equipments. You can read the value given by the instrument and convert into pressure. Okay, this is barometer. Okay, this is a barometer. So what do you use? What is barometer used for? Is for measure atmospheric pressure. So if you have this barometer, you just bring it outside, and from there you can calculate what is the pressure, the atmospheric pressure at your place. So if you're at mean sea level, it's saying that the pressure you can get the value of 101.325 kilopascal here, down here. You can get this value, 101.325 kilopascal. So this is the equipment here. Is this one. So it's very simple. You have like a, what do you call, a container, and then in the container you have a tube, inverted tube, and then we put mercury. And then but we have to make the complex one is to make sure this area here is a vacuum. The complex thing is to make sure that area in the tube is a vacuum, meaning the pressure is zero, absolute pressure zero. So when the pressure here is zero, outside here is atmospheric pressure. So definitely the atmospheric pressure will push the mercury inside, because the pressure of the atmospheric pressure is higher than zero. So it's going to push until, how high is going to push? It's going to push until the weight of this mercury, the weight of the mercury here, balance the atmospheric pressure, and then it's going to stop. Right? So how do you measure the pressure now? So when you put this, when you use this barometer, the height of the mercury is going to give you 760 millimeter. So, or 760 or 0.76 meter, which is 76 centimeter. So the mercury will rise up 76 centimeter if you put this at mean sea level, because of atmospheric pressure. So from there, from this value of 76 millimeter, of course you can calculate the pressure. How do you calculate the pressure? So you calculate the pressure because we know it's a different color. This is going back to basics. This is the concept. So we know the pressure here. I hope you can see my marker here. Okay, you can see. The pressure here, which is border the atmosphere and the mercury, and the pressure here, which is the pressure inside the tube but at the same level here, must be the same. Because why? Because it is the same elevation. Because it is the same elevation and it's connected by the same fluid, mercury. It's the same elevation and it's connected by the same fluid, so it's the same pressure. So now we have to figure out what is the pressure here. The pressure here, because you know here the pressure here, the pressure here is absolute pressure is zero. P equals to zero here, right? Because this is vacuum. So when you want to find the pressure at the bottom here, the same equation as before. P at the bottom so P at the bottom here, let me call this as 0.1 here, not bottom of the container here, this point, 0.1 here. P1 equals to P at the top there, which is P vacuum, plus the equation we learned just now, rho G H. So you can know P vacuum is 0, plus by rho. Rho is what? Density of the mercury lah. You have to know what is the density of the mercury. So the density of the mercury is, what was it? 13,560 meter cube per second times by gravity, which is 9.81 meter per second square. And then you times by the height difference from here to the point, 2.1. We know the height difference is 0.76 meters times 0.76. So from here, you will get 101.325 Pascal. So from here, you will get 101.325 Pascal. So the concept is just balancing the weight of the mercury, which is the rho GH, with the pressure outside. Okay, so this is another question. Why are we using mercury? Why don't we use water, for example? Why do you think we use mercury instead of water? Higher density, right? Mercury has higher density, but why? Then why? Agree, water has lower density, mercury has higher density. So, exactly. Thank you, Yihan. Because if you use water, it's going to rise up instead of 0.76 meters, which is less than 1 meter. It's going to rise up 10.3 meters. Do you know how high this 10.3 meters is? Almost 3-story building. 3-story building, 10.3 meters. So you don't want to use an equipment which has a tube of 10 meters high. So it's not practical. So that's why they are using mercury, because of the higher density. Right? So this is a bit, it's more towards being practical. If you want to use water, go ahead, but you have to have a tube of 10.3 meters high or 11 meters high. Okay, thank you. So these are examples of barometer. You have like manual barometer, you have digital barometer, and then you can have your make yourself barometer on the right side here. So this is some link that you can have a look. So we have looked into barometer. Now piezometer. What is a piezometer? Piezometer is to measure pressure in a pipe. Pressure in a pipe. You want to measure pressure in a pipe. So let me go to the next page here first. So this is example of a digital analog piezometer. So you have your pipe here, and then you put a manometer, and then in this case they put some reading here. So as the water flows, there's pressure, so the pressure will be read by this manometer, or piezometer. So this is how it looks like. Right. So going back to this original diagram, so this is the pipe here. This is the pipe. And then you have this piezometer here. You put some piezometer. So because at this point, at the center of the pipe, you have pressure, it's going to the water will go into the piezometer at some height. So at some height. So the liquid will rise because is going to balance between the pressure here and the atmospheric pressure here. Here you have atmospheric pressure at this surface. You have atmospheric pressure. So what's the equation? Again, the same concept as before. Let me use my pen. You want to find the pressure here. Let me call this point 1. You know the pressure here. Let me call this point 0. So pressure at point 1 equals to pressure at point 0 plus rho GH, the same concept. All right. Okay, now P0 here. Now, when we deal with pipes, we can, if you remember, we have absolute pressure, which is the real value. Atmospheric pressure is 101.3. That is absolute. And then we have gauge pressure. So when we deal with pipe, we use gauge pressure. So gauge pressure is 0, right? So gauge pressure for atmospheric pressure is 0. So you will have 0 plus rho. What rho are we using? Density. We are using the density of the liquid in the pipe. If it's water, then you use density of water. Times G, gravity, times H. H is the difference of elevation between point 0 and point 1. So here, you have down here, rho GH. So from the height of the water of the fluid in the piezometer, you can read the level, and then you can convert into pressure. So this is piezometer. Pressure in pipes is important because we have to monitor the pressure in pipe so that one, it has enough pressure to move the fluid towards intended customer. If the pressure is too low, the water will not arrive in our houses. Second, if the pressure is too high, it might damage the pipe. So we have to monitor the pressure. So this is one way of monitoring. Dekat atas tangga. Dekat atas tangga, pokok di atas. Right, sorry for that. Right, next, continue. We have this piezometer. This is two piezometers connected. Right, they have two piezometers connected. So this is a pipe. The water, I'm assuming the water is moving from left to right. Right? Okay, good. That's the direction. So you have the piezometer 1. This is the piezometer 1. And then you have piezometer 2. It's connected. And then you have air pressure here. Right? It's connected. You have air pressure. So if you look at the last equation here, if you have two piezometer connected, what you can get is the difference in pressure. You can get the difference between pressure at point 1, which is here, and the pressure at point 2. You can only get the difference. You can't know what is P1. You don't know what is the pressure at 1. You don't know what is the pressure at 2. But what you know is the pressure of difference. Right? So if you look at the first equation here, P1 equals to rho GH1 plus PA. So P1 here, the bottom here, is equals to PA. What is PA? Here, the pressure here. PA plus rho GH1. Rho GH1 is, rho is the fluid density of the fluid, gravity. H1 is the distance from this surface towards point 1, H1. Straightforward. What is the pressure at 2? Pressure at 2 is also atmospheric pressure, air pressure, PA, also PA here. But now plus rho G H2 because the distance from this point to pressure at point 2 is only H2. So now you have the equation for P1, you have the equation for P2. So you subtract equation 2 from equation 1, you just subtract. Why do we subtract it? Because we want to remove this PA. Doesn't matter what the value of PA, we just remove it, to make things simple. We subtract 2 to 1. So when you subtract 2 to 1, your PA and PA will cancel each other. And then you will have P1 minus P2 on the left hand side. On the right hand side, we have rho g H1 minus rho g H2. And then here in the diagram, they have simplified things. They say that H1 minus by H2, you get H. H1, which is the longer one, minus by H2, you get H. So they simplify P1 minus P2 equals to rho g H. So just by reading the difference of height between tube 1 and tube 2, reading the difference of height, you can get the difference in pressure between P1 and P2. Right? Now the question will be, here they call this as PA. Here also, they assume PA, meaning what they are assuming is the pressure here, here, all the pressure of air pressure in this white area, doesn't matter which elevation, is the same. They are assuming this is the same. So this question, why the air pressure they are assuming the same, even though at the elevation is different, is the same question I asked before for this example. The same explanation applied for both, right? So again, if you have the answer, you can WhatsApp me. If you have any question, you can ask by just turn on the mic. But the concept is the same, right? This concept is very simple. This is the concept. Pressure at some point must be the same as pressure at a point that you know the value. In this case, PA plus by rho GH, plus by rho GH. Plus, because plus, why plus? Because we are going deeper. If you're going higher elevation, so you minus. Don't forget that. Because as you go deeper, the pressure will increase, so you plus. As you go higher, the pressure will decrease, so you minus. Right? So this is the same concept again, but this is manometer now. Pressure measurement number 3, manometer. To pressure, also when you have two tubes, you can only measure the pressure difference, meaning you can only measure the difference between pressure at point 1 and point 2, or point A and point B. You can't really get the pressure, what is pressure 1, what is pressure 2, you don't. Okay. So here, there's a pipe. Actually, there's a pipe here. There should be a pipe. Let me just draw this pipe so that you can get a better understanding of the diagram. Let me draw the pipe. Let's use black color. Actually, this should be connected to a pipe. Like that. And then the water is moving from, in this case, it's moving from left to right. So this is a pipe, right? It has a pipe, and there's two tubes connected. So we call this as manometer. So at the center here, we can call here, at the center of the pipe, we can call point A. Above this tube, at the second tube above it in the middle of the pipe, we call it as point B. So now we want to know what is the difference of pressure between point A and point B. So what is the difference of pressure between point A and point B? Now, this is a little bit more complex than before, because here you are dealing with some liquid and you are dealing with air. But this one, you are dealing with some liquid. You are dealing with two liquid, the liquid in the manometer and the liquid in the pipe. So it's not air anymore. So you have two liquids. So because of that, you have two density of the liquid in the pipe. Let's assume water, and density of the liquid in the manometer. They call it as rho of manometer, rho m. So you have two density now. But you don't have to worry. The concept is still the same. What you have to do now, figure out what PA is. So let me draw here. How do you get PA? PA, or instead of doing that way, let me try to Okay. Let me make some adjustment first. Because there's a few A there. The bottom here is already point A, and then I call this point A2. So let me just remove this and call this as point 1 and point 2. Point 1, point 2. Right. So this is PA. Let's figure out. Okay, now always the first step, if you have 2 manometers, pick 2 points that you know the pressure is the same. Pick 2 points that you know the pressure is the same. So if you remember, for it to be the pressure to be the same, it has to be the same elevation, and it has to be connected by the same fluid. Or let me give another requirement. It shouldn't be moving. It should be static. It should be static, not moving. So the water, the liquid in this manometer is not moving. It's not moving. Only the water in the pipe is moving. So this water in the pipe is moving, but here in the manometer it's not moving because it's static. So based on these 3 conditions, I can say that this pressure here, pressure A, and the pressure here, let me call this as 0.3 lah. So the pressure at point A and point 3 is the same. The pressure at point A and point 3 is the same. Okay. Okay, so now we have picked 2 points which has the same pressure because it has the same elevation connected by the same liquid, which is the manometer liquid, and it is not moving. I mentioned not moving because 1 and 2, point 1 and 2, it is the same elevation. It's connected by the same liquid, but it's moving. It's a moving fluid. So the pressure can be different. So I have to mention not moving. So now, what is PA? So PA must be equals to, let's pick a point. Let's pick point 1 here, because in the end, we want to know the pressure difference between point 1 and point 2, right? So let me pick point 1. PA equals to P1 plus rho GH, rho GH. Rho of what? Density of what? We are talking about this liquid here because point 1 is here, point A is here, so we are talking about this rho GH. So the liquid here is rho of some fluid. Let's just call it rho times G times by H. So let me call this H as what? What can I call this as H1? Let me call this as H1. The difference of elevation between point 1 and point A. So rho G H1. So that's the first equation. So this should be straightforward. Rho G H1, right? So we have the equation for PA. What is the equation for pressure at point 3? What is the equation at pressure at point 3? Equals to, let me start at point 2. So P2 plus, because we are going down. Okay, now from point 2 to point 3, actually there's 2 liquid, right? You have the liquid of the pipe and you have the liquid of the manometer. So you have to split into 2. So let me call this distance. Let me just call this distance here. From point 2 to point B, let me call this as H2, for example. So now we have P3, the pressure down here at point 3 equals to pressure at point 2 plus rho of liquid in the pipe, G. The distance is H2. Because we are taking only until point B. H2. And then you plus again, because we are not finished. You plus again this part in the manometer part. Don't forget the manometer. So you have 2. rho m, because the density of the fluid in the manometer is rho m. I'm struggling with this rho m g, and the height is h. Okay, now you already have the pressure equation for point A and for point 3. Right? You have equation point A and point 3 now. So up to this point, do you have any questions? Do you understand? If you need me to repeat, I can repeat. Thank you. Thumbs up from Intan, Anas, right? Okay, now, so you can figure out now our aim is to get the pressure difference between point 1 and point 2. So from here, you can cancel each other lah, eh? Okay, you have a few ways to do it, but how about we equate? We know pressure at point A and pressure at point 3 is the same. So we equate equation 1 and equation 2. PA must be the same as P3, meaning what is PA? PA is P1 plus rho G H1. I'm just using my mouse here. Alright. I hope you can try to. This is PA, P1 plus rho G H1 equals to P3. What is P3? P3 is P2 plus rho G H2 plus rho M G H. Right. So from here, you can do a few things you can try to figure out. So I can bring my P2 to the left hand side. So in the end, I have P1 minus P2, which is what we want. Bring P2 to the left hand side. P1 P2 equals to we have rho G H2 plus it's okay, eh? You have to make some mental calculation here. So P1 minus P2 equals to rho GH2 plus rho MGH minus rho GH1. We bring this rho GH1 to the right, minus by rho GH1. And then H plus H2 is H1. H plus H2 is equals to H1, right? From the diagram, H plus H2 equals to H1. H plus H2 equals to H1. So you can apply and you can simplify further. But in the end, you're going to get this, right? This is change in pressure, P1 minus P2 equals to rho M minus rho GH. Okay, let's try to figure this out. Right, I can just straight away rho G bracket H2 minus H1 because we bring the H1 to the right. H2 minus H1 plus rho MGH, eh? Plus rho MGH, right? So we have this one. H2 minus H1 is equal to what? H2 minus H1, H2 minus H1, you get negative H. Eh? H2 minus H1 is negative H. So equals to, you're almost there. You have to bear with me. Tak boleh padam pula dah. Is it hanging? Alright. Where are we? So equals to negative rho GH plus rho MGH. And then you can factor them out, and then rho M here, negative rho here, so you can get this line. You can get this. So the change in pressure equals to rho of manometer minus rho of liquid times by G times by H. So the first concept is this one. This is the main concept here on the left side. This, you find the pressure at point A, you find the pressure at point 3, you equate them, and then you simplify it so that you can get P1 minus P2. So this is manometer, differential manometer. Right, this is an example that you can do it yourself. So this is what we call a venturimeter. Are you guys with me? Can you hear me? Tadi I nampak there's a internet problem. Okay, good. Okay, so this is a venturimeter. You have a bigger diameter pipe. The water is moving, and then you have a smaller diameter pipe. So when the water flows from a larger area to a smaller area, the velocity will increase. So the velocity at this throat, point 2, is higher as the velocity at point 1, this big larger diameter pipe. But the pressure is the other way around, right? The pressure at point 2 is lower. The pressure at point 2 is lower as compared to the pressure at point 1. So because this is Bernoulli equation, we'll go into Bernoulli equation in chapter 3, but I know you have learned this before. Bernoulli equation states that if the pressure reduces, the velocity will increase. So now, again, we want to know what is the difference in pressure between point 1 here, the yellow bar here, point 1 in the middle of the pipe, and the point 2. This is the solution. The change in pressure equals to rho M minus rho GH, the same as before. The change in pressure equals to rho M minus rho GH. So you can, the same step as before, okay, you give a number 0.4, you give a number 0.3. Why do we pick these two locations? Because these are the 2 points that has same pressure. It's the same elevation, connected by the same fluid, and it's not moving. And then you give some reference, the height from point 2 to point A. And then from there, the same concept as before, you can derive to get this one. So you can try this at home. You can try this on your own later and make sure you get this. So if you manage to get this, meaning you understand the concept. If you don't manage to get this, you can ask your friend or you can WhatsApp me. Right. So you can see at point 1 must be higher pressure because the liquid is pushing the water at a greater elevation, point 1. At point 2, the liquid is pushing the water at a smaller elevation. So you can see from here, the P1 is higher than P2. How to solve YouTube problems? Okay, this one, same concept. This is another simple manometer. You have a pipe moving from water moving in a pipe from left to right, and it's connected by simple manometer, but here it's open to the atmosphere, meaning gauge pressure 0. Same concept as before, exactly the same concept as before. Figure out what is point 3, figure out what is point 2 here, figure out P3, figure out P2, equate them here, and then you can get. But now the equation is bigger. What the pressure at point P is equal to rho mg delta h. Rho m is the manometer here. Delta h is the difference of height between this point and point 2. minus rho GL. So it's much more complicated here. But the point being is, if you have this simple manometer, you just read the L. What is L? You just read the delta H, right? In the lab, you just read the L, you just read delta H, and then you apply this equation to get the pressure. Okay. How do you get this equation? You have to derive based on the understanding here. You can try this at home, but hopefully the concept you understand. Do you understand the concept? There's no thumbs up. Or do you need me to explain a little bit on this part? Can you guys hear me? Boleh dengar ke? Marisa, can you hear me? Boleh dengar ke Marisa? Okay, boleh, no problem. Marisa baru nak cakap. Boleh dengar ke Marisa?
Boleh, Doktor.
Right, thank you. Okay, same concept as before.
Excuse me.
Yes, Anas.
I just want to check the delta H is the height difference, right?
Exactly, the height difference between 0.1 and 0.2.
Okay, sure.
Sure, right. Okay, then I will go through. You have a few ways of doing it because this is more towards mathematics manipulation from the concept. So for my part, I always pick the 2 point that has the same pressure. So from this diagram, the 2 point that has the same pressure is 0.3 and 0.2 because it has the same elevation, it is connected by the same liquid, and it's not moving. So these three principles. So that's why this is the first equation, P3 equals to P2. So now figure out what is P3 with respect to what? With respect to P lah. With respect to P. So P3 is equals to P plus rho GL plus rho GL plus rho GL is the pressure or the weight of liquid between P and 3. So rho GL. Which rho are we talking about? The rho of the liquid in the pipe. Right? That's P3. P3 equals to P plus rho GL. The same as before. Are we okay on this part? Siapa tadi? Intan. Oh, Nur Amira, sorry. Nur Amira aku yang tanya tadi. Nur Amira, okay ke? This first part? Right, okay. Now, for P2, we have to find what is P2. P2 is, we pick a point, so we pick P1 because P1 kita tahu, doesn't matter lah, we know the value or not. We pick P1, which is P1, plus the weight of the water between 0.1 and 0.2, rho GH. Rho of what? Rho of this liquid, the blue liquid, which is, we call this as rho M. G, what is the H? In this case, they define it as delta H. They define it as delta H. You can just use H, no problem. You can use delta H, you can use H, you can use Z. It's just a symbol. So what is P2? P2 is P1 plus rho GH, rho of M, the blue one, and the distance delta H. So now you have P3 and P2. So our aim, so you equate, we remember this equation, P2 must be equal to P2, P3 must be equal to P2. So you equate, so rho GL plus P must be the same as this one. So this is what happened. So in the end, you want to get P. So you rearrange so that P is the subject. So P equals to this one. And this one is missing. Why P1 is missing from this equation? Amira, kenapa P1 is missing from the equation? This P1 here. P1 ni dah hilang dah. P1 dekat sini. This is P1. Exactly, because P1 is atmospheric pressure. So kalau kita guna gauge pressure is equal to 0. So we can just ignore it. So that's how you get this equation. Hopefully that clears this equation. Again, this is the important part is this one, the concept tu je. Pick a point that has the same pressure and find the equation for that point using P plus rho GH. P at some point plus rho GH. P at some point plus rho GH. So that's the equation. Same concept. Again, exactly the same concept here. So this is actually, if you don't understand the diagram, this is actually a pipe. They hang. This is actually a pipe, but it's a cross section. We are looking at the cross section of the pipe. So if I draw the longitudinal part, the pipe is something like this. The pipe is going that direction. Yeah, that's the pipe. The water is going, let's say, into this diagram, going that way. But now at the side of the pipe, we put some, we what do you call? Insert some tube. So we want to know the pressure. So the pipe is going that way. So we are just looking at the cross section of the pipe here. So you want to know what is the pressure here. They call it as P1. P1. But we want to know what is the pressure in the pipe. Of course, we want to know the pressure in the pipe. They call it as P1. Alright. So how do you get P1? Again, okay, maybe this one I have to explain a little bit. How do we get P1? Again, find 2 points that has the same pressure. So I want to use point P and point Q because the same elevation connected by the same black liquid and it's not moving. So what is the pressure at point Q? So here, pressure at point Q must be the same as this one here, PA plus rho GX. PA, because this is PA, here is PA, plus rho of this black liquid. The rho of this black liquid they call as B, rho B, G, the distance is X. So you get this one. That is PQ. Now we have the first equation. The second question, what is PP? Pressure at P. Okay. Can I ask you the pressure here, the pressure here, the pressure here, the pressure here, the pressure here. Is it different? Pressure here, 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 here. Is it different? Yeah, it's not different because it's the same elevation. Same elevation, the same liquid. And here is not moving. Here is not moving. The water is moving only here. But because here we are measuring the pressure here, so it's the same. So it's the same. So what we can do now is instead of P1 here, in the pipe, we can put the P1 here. Right? This is P1. It's the same. Right? So now, what is P? P at point P. P at point P is equals to P1, the pressure here, plus rho GH. Our rho of this liquid, the grey liquid, which is A, rho A, G, and the distance between 1 and P, which is Y. So we have rho of A times G times Y. So that's why we have this equation. P at P equals to P1, pressure 1 here, point here, plus rho Gy, rho A Gy. So now we have pressure at P. Now we have pressure at Q. So, and we know that pressure at P must be the same as pressure at Q. So you can equate them. So P1 plus rho A Gy is the same as PA plus rho B Gx. So here. So you can rearrange, because in the end we want to get P1. So rearrange P1 as a topic. So you rearrange, you get rho Bgx minus rho Agy. PA is 0 because here, point A here is open to the atmosphere. So we can use PA equals to 0. Assume PA equals to 0. And then if A is gas, if the pipe is filled with gas, I don't know, maybe some oxygen tank, moving oxygen or moving nitrogen is a gas instead of water or oil, is a gas. So our density of A is density of gas, but we know, but B is a liquid. B is a liquid. So rho of A is so small compared to rho of B. Let's talk about water. Rho of B, if it's water, the rho density of water is 1000 kilogram per meter cube. Rho of, let's say, air is only 1. So 1 compared to 1000, so density of A is very small. So you can assume rho air is not significant. You can just ignore this term. You can remove rho A is very small. You can ignore. So P1 is rho Bgx. Okay. This one, P1 equals to the pressure in the pipe. The pressure of the fluid in the pipe is equal to rho of B times G times X. X is where? Here. But this one is only if the pressure, only if the liquid is a gas. As if the fluid is a gas. If it's liquid, you can't assume this. You have to use this equation here. The full equation, rho Bgx minus rho Edy. Okay? Right. This is some self-test. Please, I'll give you like maybe 5 or 10 minutes. Right? I'll give you 10 minutes. We can take a break. I mean, like take a break while doing the example. We take a break while doing the example. I'll give you 10 minutes or 15 minutes to figure this question out. Please try to draw it on a piece of paper, and then you can share in the WhatsApp group your solution. You can share the solution in the WhatsApp group, or if you want to turn on your camera and show your solution. So I will just pick one or two of you to share your solution. Okay, let's go to the question first. The YouTube manometer shown in the figure. So YouTube manometer, we are referring to this one. This one. YouTube manometer is used to measure the pressure in a pipeline. So we want to measure the pressure here. We're using this manometer. This is a pipeline. Here, this is a pipeline. As it passes over the crest of a hill, this is not important information. The pipeline carries fresh water. So the pipeline is fresh water. Density is given. Density of the water in the pipe is 1000 kilogram per meter cube. The bottom of the U-tube contains mercury. So here, this black manometer fluid is mercury. The density is 13,600 kilogram per meter cube. Taking atmospheric pressure as the equivalent of 10.3 meter of water. Okay, now P1 is atmospheric pressure equals to 10.3 meter of water. Yeah, the unit is meter, 10.3 meter of water. So you just convert into rho GH lah. Rho, let me erase rho GH because 10.3 meter is the H for the atmospheric pressure. We're talking about for the atmospheric pressure. Rho of water, because we are talking about 10.3 meter of water, times G times 0.3. I mean, if you calculate this, you will get the atmospheric pressure value 101.3 kilopascal. Kilopascal. Be careful of the unit, or 101,300 pascal. So that's the pressure here. The pressure here, atmospheric pressure. With the readings shown in the diagram, so take the atmospheric pressure of 101,300, and then you have this reading 0.1 meter here, and then you have 0.5 meters here. Calculate the absolute pressure at the center of the pipeline. Calculate P, the pressure at the center of the pipeline, but absolute pressure, meaning, what does it mean? Instead of you assuming the atmospheric pressure, P2 here, instead of assuming it to be 0, gauge pressure, you cannot assume gauge pressure. You have to assume absolute pressure, 101,300. Okay? So I'll give you 10 minutes and we take 10 minutes rest. After 10 minutes, I will call a couple of you to share your solutions. If you have anything, you can ask. If you have anything to ask, you can ask in the chat or through the mic. All right. Hello. Okay. Who would like to share the solution first? Wen Yen, are you around? Maybe Wen Yen or and also Teo Di Wei. Do you want to share your solution? You can either well, you can explain. Never mind. You don't if you don't get the answer, it's okay. Let's try to go through and we discuss. How are we going to do this? Are you going to share in the WhatsApp and then I can or you can share your screen. Yeah. All right. Okay. Let me. I will share. Okay. Try to share in the WhatsApp first. It's okay, Theo. You can just share your whatever you have, then we can discuss. Or you can share your screen. Boleh je. You want if you want to share your screen. Sekejap je kot. Okay, good. So how do I do this? I need to go out from here. Stop sharing kejap. Let me stop sharing. Let me go to the WhatsApp document. Who is this? The one is Theo. One is download. Right. Thank you. Photos. Okay, just once. All right, nice. What do we do? Share screen again. Where is my Webex? Share screen. Share. Right. So I hope you can see this is Wen Yen's solution. Alamak, macam mana saya nak buat ni ya? Because nak side by side dengan gambar lah Macam mana nak buat? Pun PowerPoint kejap. How do I do? Kejap. Point. This is the PowerPoint. That's where is the solution. Download. Here. Bring it here. Okay. Please bear with me for a second. Okay, I think we got it now. Okay, right. Right. P3 equals to P2, which is correct. The 2 points that has the same pressure. P1 equals to 0 equals to P2, right? P1 equals to P2. But we have to, instead of using gauge pressure here, because the question asks for absolute pressure, so you have to change this. Instead of 0, you have to use rho. I think maybe you haven't applied. I think you haven't applied because I think you assume 0. You have to rho of water because it's saying 10.3 meters of water. Rho G 10.3, which will, I think, will lead to 103, 101.100, 1,300 kilopascal. Sorry. Okay, that's the first one. Instead of using zero gauge pressure, use absolute pressure. And then what is P3? P3 equals to P4, which is correct. Plus, okay, this one, plus not rho GL total. Okay, right, okay, I understand. You have, I'm using the one before. P4 plus rho of mercury. This is a rho of mercury. G 0.1 plus rho of water G 0.4, because the distance from P to the surface is 0.4. 0.5 minus 0.1. This is correct. And then you simplify things. I'm just looking at the concept. I'm not going to calculate here. Right. And then you have P3 equals to P4. Okay, this is P3 equals to P4. P3, where is P4, right? Now P3, now you haven't, okay, you've done P3. Now you have to do P2. What is P2? You haven't finished yet. You are not finished yet. P2 equals to atmospheric pressure. This is straight away atmospheric pressure. This is atmospheric pressure. What is atmospheric pressure? Rho of water times G times 10.3 meters just now. And then you apply this equation. P2 equals to P3. So meaning P4 plus 17265.6 equals to 10130 Pascal. So you are not finished yet. So when you do that, you will get, in the end, you get P4, which is the pressure in the pipe, right? So you're almost there. You're almost there. Okay? Are we okay? Do you understand? Right. For apa ni? Theory way. Saya kena smallkan sikit kejap. Right. So okay, I see P2 equals to P3 here. Ni tak boleh conteng lah pula. I kena guna tulis je lah PDF. P2 equals to P3 equals to P0 plus 4905. Where do we get this? P0 plus. Okay. Okay, P3 equals to P0 plus rho Hg. P3 equals to P0. Where is your P0? When you use P0, you are assuming here, right? P4. I'm assuming P0 is here. Plus rho GH. Rho 1000, 9.851, 0.5. Okay. This is the mistake. Because from P0, the pressure in the pipe, or P4, here, to P3, you have two liquid, the water and the manometer. So you have to split two, like when Yen did just now. So you have rho of water G 0.4 plus rho of mercury G 0.1. So that's you need to rectify here, right? And then P2, P1, where is P1? Okay, P1 equals to P2 minus rho m GH2. P2, P1, okay, rho m. P1 and P2 is the same because point 2 and point 1 is connected to the atmosphere. So we don't, if you want to calculate, you have to use the density of the air, but density of air is very small. We can neglect it. So P1 and P2 is the same. So P1 equals to P2 equals to rho of water times G times 10.3 just now. Okay. So you have to make some changes here. Okay. Hopefully, anybody wants to share their solution to discuss? So I'm not sure whether it's in the notes or not, but here is the step-by-step guide. Step-by-step guide. So we understand this P1, P2 equals to P1 equals to 0. Gauge pressure. This is gauge pressure. We understand this. P3 equals to P4 plus rho mg 0.1 plus rho wg 0.4. And then we equate P2 and P1, P2 and P3, sorry. So you have 0 equals to P4. Here, for the time being, I'm using gauge pressure 0. Not a problem. But later on, if I want the absolute pressure, whatever result I have before gauge, I just add atmospheric pressure. You can do that. So you can use atmospheric pressure later. You can add on the atmospheric pressure later. If you want to calculate using gauge pressure first, also you can do it, meaning P1 and P2 0. Just calculate and then you get P4, but that P4 is gauge pressure. If you want to get P4 absolute pressure, you plus by atmospheric pressure. Right, thank you for sharing the solution. The answer is there. You can try. If you don't get it, you can just WhatsApp me. Right. So this is work example number 2. Where is the work example number 2? There's no solution here. What is the solution? There's no solution here. But there is step by step here. So you can do example number 2, and then if you have problems, also you can WhatsApp me. Right? So I'm just going to skip the same concept, as before. But now they are using specific gravity. They don't give you the density. They are giving you the specific gravities. So for the gray one, the specific gravity is 1. For the red one, the specific gravity is 2. So you have to convert from specific gravity to density. So you have to remember the equation. Specific gravity is the ratio. The ratio of density of the liquid that we want over density of water. So this is another step by step. Okay. I think I'm just going to skip this. The same concept as before. Exactly the same concept. You can have a differential U-tube. So in the end, you get P1 minus P2 equal to rho m minus rho GH. This is exactly the same as the venturi meter before. Rho m minus rho GH. And then you can have differential multimeter inverted, and then has angle also. But you don't have to worry about the angle, because in the end, we just worry about the vertical distance. We just worry about the vertical distance. Also, I'm going to skip this part. You can try to understand this. If you don't understand, you can ask me later. You have to try. You have to try do it on your own. Then only you can understand. If you just look at this, you won't understand. Just try. Step by step, try this. So this is another problem. You can do this exercise. So I think you better do this exercise and then submit to me. Let me take note. You have to do this exercise 1. The equation, the values are all there. I think the question is find the pressure, the pressure in the tank, because this tank is not open to the atmosphere. So it's pressurized tank, pressurized by air. So find the determine the air pressure in the tank. So try to figure this out. You have water, you have oil, and you have mercury, and then open to the atmosphere. So please do this exercise and submit by when? We don't have any class next week, so submit before 2 weeks from now lah. So when we meet physically, so next week no class, then we have our physical class. When we meet physically, please submit this on a piece of paper, hard copy. Do on a piece of paper and submit in the class. You don't have to don't submit online. Just on a piece of paper and submit the solution there. Right? Everybody okay? This is your first assignment. Right. Okay, now we are going to the second half of the topic. Hydrostatic chapter 2 is majorly divided into 2. Pressure measurement, the first part that we have gone through just now, pressure measurement, understanding the concept of pressure and manometer tube. And the second one is now we are looking at the important one, which is the hydrostatic force. So if you look at the diagram here, this one is a dam. You can assume it to be a dam, wall dam. And then this gray here, gray dot 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 here, gray hatch here is a liquid water. So you can have hydrostatic force. Hydrostatic force increase linearly with depth. That's why you have this triangle. Triangle. Also, you have atmospheric pressure on the left side and on the right side of the dam. But because they cancel each other, the atmospheric cancel each other, so we don't have to think about it. So this is the pressure that we are concerned with. This is the pressure that we are concerned with. So these are pressure. Rho GH is pressure at one point. Right? Remember rho GH? My full screen. P equals to rho GH is a pressure at one point. So if my point is here, so my rho GH is from the top, is from here to here. Right? That's my H. If I want to calculate what is the pressure at the bottom, if I want to calculate the pressure here, rho GH, what is the pressure here? My H is from here to here, right? So rho GH is the pressure at one point. But now we want to calculate the force because of all this pressure at all points continuously. So you know the equation, force is pressure times area, because you know pressure is force divided by area. So force is pressure times area. So the pressure, we know that pressure is rho GH. So if P equals to rho GH and then times by A. Okay. So A, what is A? A is the area of the force that we are concerned with. A, if it's a square, the dam wall is a square. So area is the height of the wall, this height. This height times by the area going in. 3D, This wall is 3D, this wall is 3D going in. So you times by the width of the wall going in. 1 meter or 2 meters or 3 meters, So that's the area. So imagine this is a wall. So this is 2D, two-dimensional. If it's three-dimensional, it's actually like this lah. Right? So the area, because we are talking about hydrostatic, so we are talking only up to the surface, up to this. So this is the area that we are concerned with. This is the area. So the height times by the width, that's the area, right? This is A. Ada soalan ke? Saya terdengar ada suara seseorang tadi. Okay. Right, that's A. But for this P, rho G H, H ni at one point. So which H are we taking? Are we taking the whole H, H at the bottom? Are we taking the H at the middle? Or are we taking H at the top? Because H, if you remember, rho GH is pressure at one point. Now we want to take all the pressure at all points. So which H are we going to take? So this is what we are going to figure out later on. Which H are we taking? H at the bottom ke? H dekat tengah ke? H dekat atas? What do you think? Which H should we take? before we move on? Just have a guess. Any idea? H mana nak guna? No idea eh? Then kita continue lah eh. This is the application now. We've gone through last. We have this ocean wave, and then we have this dam here. So this is the water. So this is the wall here. So you have to calculate the hydrostatic force. F equals to pressure times area. Pressure is rho GH. But we have to be careful with the H. Which H are we taking? And then times by the A. The height of the water times by the width. So in this case, if this wall here, dam here, if it's 100 meter length, so your width is 100 meter lah. 100 meter times by the height. Okay, you have a look at this picture, just a refresh. We have to, the wall has to be strong enough to withstand the hydrostatic force for this dam, empangan ni. If not, the dam could fail because of slipping or overturning, or structure failure, meaning the concrete itself fails. Right. This is the interesting part. We are going to derive. We are going to figure out the H just now. Which H are we taking? Okay, I'm going to go here this part quite fast. I mean, I'm not going to stop, but if you don't understand, you can ask me later. Right. I'm just going to storytelling, assuming I'm storytelling to myself. All right, and there's no audience. Okay, we have water. The dot is a water, and this gray object is our object. So because this object is submerged in the water, so we will have hydrostatic force in this whole object. We will have hydrostatic force in this whole object. So let me just draw. The equation force equals to pressure times area. So if you go back to your maths, I'm not sure during your form 5 or during your matriculation or STPM, usually we will take a small element first. We will analyze a small element and then we integrate it to become bigger. So in here, the same concept as we used before. We analyze a small element. So we analyze this very dark gray here element. We analyze this dark gray element first. Forget about this gray, the other object, just this element. So the size of this element is dx. The height of this element is dx. Dx usually is used for a very small element, dx. You know your dy dx, that d represent a differential element, meaning it's very small. So we are going to find what is the pressure on this small element. So you remember the equation, pressure is rho g h. So if we take this element, based on this diagram, it's going to be rho g h. In our case, it's going to be rho gx lah. Because it's very small, it doesn't matter x. It doesn't matter x at the top here, x at the bottom here, or x at the middle, because it's very small. So just take x, rho g x. So that is pressure at a very small element here. Okay, straightforward. Now, what is the pressure? What is the force for that small element? Force equals to P times A. We already have the P. What is the A? The A is basically dx here, dx times B. Dx times B. So this is why we have this one. So the force acting on the very small element is rho gx, the pressure, times by B dx. Right? So this is the force on a very small element. So you already got the force on the small element. So if you want to get the force on your whole object, what do you do? Mathematics, what do you do? Any suggestion? Oh, I'm assuming there's no audience. Okay, no audience. We integrate. Kita integrate it from the bottom to the top. You integrate it. So let's go to the next slide. So the force acting on the whole area, is rho gx times b dx. You integrate them from the bottom to the top. Okay, so from your mathematics, constant which doesn't change with dx, you can bring it out. So rho g you can bring out. So that's why rho g is out. X b dx is here. So from your physics, I'm not sure. Maybe you will learn this in your mechanics or material. I'm not sure you're taking this. Oh, well, you guys are taking a different subject, but a different course. But yes, assume this is correct. X times B integrate over dx is your first moment of area. It's the first moment of area in which integrate x b dx is equals to a times x bar. So integration of x b dx is a first moment area from your physics, which is just a, the area, times by x bar. So in the end, this is the equation. The force, hydrostatic force on the object is rho g times a times x bar. Okay. What is A? We are talking, what is A? A is the area of the object lah. Area of the whole object. This is A. This is A. Semua ni A. I'm going to do this coloring. This is all A. Right? What is X bar? X bar is the distance from the free surface towards the centroid of the submerged object. Towards the centroid of the submerged object. That is H bar. Centroid of the submerged object. So this is the most important definition in this chapter. Okay? Please don't forget this. Please remember, memorize it. The most important definition in this chapter, X bar or HC. Sometimes the book use X bar, sometimes they use HC. Is the distance from the free surface, free surface to the centroid of the submerged object. So if I have, this is my water, this is my object, I have to find the centroid of the submerged object. So this is my submerged object. What is the centroid? In the middle. If it's a triangle, it's in the middle. So what is X bar? The distance from the free surface to the centroid. Simple. If you memorize this definition, you can do it. If my object is a triangle, I have to find the centroid of my submerged object first. So my submerged object is a triangle. The centroid is 2/3 from the top. 2/3 from the top. So now I found my centroid. So what is X bar? From the free surface to the centroid. Again, if I have a partially submerged, not wholly submerged, it's just partially submerged. So you have to, the center of the submerged object. Submerged object. So I have to look only the submerged part. Only the submerged part. Find the centroid. If it's a square, the centroid in the middle. So what is my X bar? From the free surface to the centroid. Right? Just look at the submerged part. So that's easy. If you understand this, then it's going to be easy. X bar or HC. Okay. What is A? For this case, the area is the whole area because the whole thing is submerged. For the triangle, is the whole triangle. For this one, we only take the submerged one lah, because it's hydrostatic force. The above one is not submerged. It's not subjected to hydrostatic. So the area is only this one, the submerged part. So for this chapter, the equation that is important for this hydrostatic force is F equals to rho G X bar or Hc. Sometimes they use hex bar, sometimes they use Hc for this distance from the free surface to the centroid. I'm using Hc. So this is the pressure times by A. Times by A. Where is my A? This is the most important definition. This is the most important equation for chapter hydrostatic. Rho G HCA. Right? The derivation, if you don't quite understand, is okay. But I hope you understand the concept. So rho GH is if it's only rho GH is pressure at one point. So I ask you, if you want to find the hydrostatic force, which point are we going to use? So this is the answer. You use the point at the center of the object, HC. So you get rho GHC with the pressure, then you times by the area, submerged area, you get the hydrostatic force. Right. And then another concept. If you look at this diagram, just ignore all. You already know how to calculate pressure for the whole object. For the whole object, F equals to rho G HC or X bar. Okay, here because this is using X bar, let me use X bar. So that is the same as the figure. Rho G X bar times by A. Hello, can you guys hear me?
Yes, doctor.
Okay, sorry. Okay, I'll continue. Sharing. Okay. If there's any problem with the internet, just WhatsApp me. Because sometimes when during the PKP, I didn't know that I was disconnected. I was talking to myself. Right. Rho G X bar A. Okay. This is the force. Okay. So the force, force is pressure. Let me go back first. Okay. If you see pressure acts at the whole surface. But when you already calculated force, it's going to act at one point. Rho GHCA, when you calculated force is only at one point. It's not at the whole. I mean, you can what you call resultant it into one point F. The resultant force is at one point F. So now you have the value of F, rho GHCA, but now we want to know the location of the F. Where does it act? So from this diagram, the location of the F, when you have F, the value of F from this equation, the location is not at the centroid. It's slightly below. It's at a point where we call as CP. So the pressure will be here. Oh. Come on. The pressure will be at a point we call as CP. We call it as the center of pressure. So here. Right? So you have two different, two C. The first C here is the centroid of the object. The centroid of the object where you used it to identify X bar. Right? You use it to identify X bar, the C here. Centroid of the object. Once you have your F, you need to calculate CP. You need to identify where is CP, center of pressure, because this is the location of where the pressure, the force acts. So now we go to the next slide. So this is the equation. The derivation. I'm not going to go through the derivation. So let's just go straight away. I'm going to skip this. If we have time, I will re-derive this during our physical class, not now. So the equation in the end, this is the equation. This is the equation, this one. The right hand side here is quite complex, but over time you will memorize. The equation is, let me go back to this diagram. Where is the diagram? Right. The equation is this H bar, they use H bar. Sometimes they use H bar because the H bar is the distance from the free surface to the CP, to CP. Sometimes they use H bar, sometimes they use HP. Distance to the center of pressure, doesn't matter where. So the equation is HP or H bar equals to HC plus second moment of area of the object sine square theta, sine theta square. Oops. Sine theta, but you square this. So usually we put a symbol in the middle here, sine square theta, divided by AC A. Okay, so this is the equation H bar, which is the distance from the free surface towards CP, is HC. What is HC? You know HC just now, X bar. X bar or HC, meaning the distance from the free surface to the centroid of the submerged object. IXX is second moment area. Second moment area of the object. If it's a square, the second moment area of a square is PH cube over 12. Have you come across the second moment area before in your previous subject or in your foundation? Ada ke? Pernah jumpa tak second moment area ataupun dia panggil apa? Second moment of area. So it depends on the shape of the object. And then sine square theta. Theta is the angle. If this object is at an angle, meaning if your gate is like this, so this is 90 degree. So sine of 90 degree is 0. Sine of 90 degree is 1. So you can just this one is 1. But if you have object which is like this, some angle here, 30 degree, so the pressure, the force will be this direction. Because if you remember, the force or pressure always act perpendicular to the object. So this 30 degree, you plug into this. A is the area of the object. So you have to use this equation to identify the point where the force acts. So there's a few things now. First of all, we want to know what is the hydrostatic force. We use this equation here, rho g x bar or HCA. X bar, you have to memorize the definition, is the distance from the free surface to the centroid of the submerged object. A is the area of the object. So you get F. So you get hydrostatic force. Once you get hydrostatic force, we have to determine the location of the hydrostatic force. You have to find HP or H bar. So this is the equation, Hc plus second moment area times by sine square theta divided by HCA. Then you can get the location. So that is being explained here. Here, they are using Y. Why they are using Y? YCP, because this Y is the inclined distance. It is inclined. But you don't have to use Y. We use the vertical distance, HP. So from Y, we convert into HP. Here, what is this light doing is just converting from Y, inclined distance, towards vertical distance, HP here, HCP or HP or H bar. Oh, okay, this is confusing. There's a lot of formulas around. Right. This one I should use H bar or HC. It's okay. This is HC, This is HC, this is HC. Right. Okay, this is the second moment of area, IXX or IYY here. So this is just a slide to show you how they calculate I, second moment of area. Second moment of area. So you can ignore this slide first, and you can refer to this one. If it's a rectangular, this one, the centroid, this plus is a centroid, is half from the top. The area is B times H. The second moment of area in the middle is BH cubed over 12. B is the width. H is the height. The height is power to the power of 3 divided by 12. So you can just refer to this table to find the formula for the centroid and also the formula for the second moment area. If it's a right triangle, for example, if it's a triangle, the centroid is here, is H over 3 from the top, the location of the centroid. The second moment of area is BH cubed over 36. That's the formula, where the B is the width, H is the height. So you can get the second moment area from this table, from this diagram. You can get it from there. Okay, this one, let me just go browse through the slide. Okay, I think before we go to that one, let's try to look at this example first to make sure the understanding is there. Right. You have a rectangular gate is 2 meter wide and 3 meter high. This is the rectangular gate, 2 meter wide and 3 meter high. Okay, clear. It hangs vertically with its top edge 1 meter below the surface. So this one, the gate is submerged 1 meter below the surface. So the whole gate is submerged. calculate the pressure at the bottom of the gate. So just without looking at the solution, let me discard here. Let me discard first. Let's try to insert. Just to remove the solution, let's try to figure this out on our own. Not test form, mana kita punya object. Right. So the first question is calculate the pressure at the bottom of the gate. So he wants the pressure at the bottom of the gate, which is 1 point. So simple lah, eh? It's very simple. Question A, P pressure at the bottom is just rho GH lah. Rho GH. I'm sorry, equals to, because this is dealing with water, our density is 1000 times by gravity. Oh man, this is a mess. Mana ni? Oh, hang it up. Oops, what happened here? Rho GH, which is 1000. I'm just going to spell it out. 1000 times G times H. H is 4 meters lah, because it's 4 meters submerged. I think I just should better show the solution. Rho GH, so you calculate, you get the pressure at the bottom is 39.24 kilonewton per meter square or kilopascal. Okay. Now calculate the resultant hydrostatic force on the gate. You want to find the resultant hydrostatic force on the gate. So remember the equation, F equals to rho GHCA. Rho GHCA. So rho is 1000, G is 9.81. HC, the distance from the free surface to the centroid of the submerged object. You have to find the centroid of the submerged object first. So this is a rectangular. So there's a centroid for a rectangular is in the middle here. 1.5 meter from the top. So HC is Y bar here. HC is 1 meter plus 1.5 from the surface to the centroid. So that's why you have 1 plus 3 divided by 2. And the area is, what is the area of the rectangle? 2 times 3. So the equation, the resulting is 147.15 kilonewton. So that is your hydrostatic force. So it's easy, eh? Are you okay with the solution here? Is it okay? Is it clear? TOC, okay, eh? Rho G HCA, clear, very clear. Rho G HCA. Find your HC and then it's clear. And then if the question determine the depth at which the resultant force X. So determine the depth at which the resultant force X. So we want to know where is the force acting. So we have to find HP just now. Or in here they call it as YCP, HP. So the equation, okay, the equation is this one, or you can use HC plus IXX sine square theta divided by HCA. But because our theta is 90 degree, the gate is 90 degree. So sine of 90 degree is 1. So they just remove the 1 here. They just remove the 1 here. So you only have IXX times 1 divided by HCA plus Y bar. Let me just write the equation, that another form of equation, HP equals to HC plus IXX sine square theta, but I'm just removing it because it's in 90 degree, divided by HCA. We already have our HC just now. Our HC is 2.5. 1 plus 1.5. We also have our A. Our A is 6. So we just need to find this, IXX. IXX is BH cube over 12. For rectangular, BH cube over 12. Our B is the width is 2 meters. Our h is 3 meters. So you just apply, you get 4.5 meters to the power 4. And then just plug in all the value, you get 2.8 meters. Right? So your y bar is 2.5 meters. Or your HC is 2.5. Your HCP is 2.8. So your HCP will always be larger, will always be deeper compared to your y bar. Will always be larger because if you look at this term, this is the additional term here. Alamak, dia hang kejap. Here, alamak, still hanging. Oh, baik. Oh, habis berkecamuk dah. Going back, let me go to the equation. Where is the equation here? This equation. If you look at the equation at the bottom here, HCP equals to H bar or HC plus IC sine square theta. This term is the additional term. If I remove this, HCP will be equal to HC. But because we have this term, so HCP will always be larger than HC because we have this additional term. Right? This is another diagram showing the centroid, showing the second moment area. So it's the same. It's always the same. Okay. Before we end the class, where do we go? Right. I think I'm gonna end the class there for today. Do you have any questions?
No, Doctor.
Thank you, Intan Maisara. But I will give you, we already have an exercise that you have to submit physically on a piece of paper during our, what do you call, physical meeting 2 weeks from now. But at the same time, I will give you another 2 exercise for you to do and also submit next 2 weeks. So in the end, total you have 3 hard copy to submit. So because I'm finishing the class earlier, so you have like 1 hour to do this at your own time. So I will give in the WhatsApp group and we'll continue next time. So I think that's it. Please go through the notes. There's a few things that I skipped during the class, but we will touch on that later on. And we have to arrange what we call additional class to replace our next week class. I'm not sure because you guys are from different courses. I'm not sure whether it's going to be easy or hard to find a time for that class. I hope maybe you can list the times that you guys are free for every course. For example, just list a few times, then we'll try to figure out which one that we can use to for the additional class. Right, I think that's it. If there's no question, I'm going to stop the class today. Do we want to take a group camera picture again? Boleh ke? Yay, thank you. Tan, open. Tan, I saw you opening the camera. Any of you in UTM? Anas, you're not in UTM. Where are you? Where are you? You still muting. Oh, you're in KL, right? The others, not sure. Kejap je, kita nak ambil gambar je. That's in UTM kan? No. Shi Shuyan. Not UTM. No. Okay. Yang lain, the others, are you going to turn on your camera? Yes, thank you. Siapa tadi? Theo, dia in. Bear, Yang, Yimi, Amira, Marisa, Chan, Teo, Intan. Cepat-cepat before. Okay lah, yang mana ada lah Yang ni kira dapat, yang tunjuk gambar ni kira dapat bonus mark lah nanti. Kejap, let me share in the group. I don't know how to do this lah. I'm very slow at these things. Let me take it one more time. Kenapa dua sekali tu? Alright, thank you very much. Also, I'll see you guys next 2 weeks. Selamat berbuka, happy iftar, and Eid Mubarak to